Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tare, and this is my continuing series on the Math Lovers book. I'm up to section 3.4 of volume 1, which is on Fibonacci numbers and the golden ratio. And this is my fifth video on this section, and it's on what are called metallic ratios. And this is going to be a pretty short video. I'm just going to define what metallic ratios are. They're analogues of the golden ratio, which I talked about the last few videos. Anyway, let's begin. So, how do we define a metallic ratio? Well, like I said, the golden ratio I already talked about. That's actually, you can think of that as the first metallic ratio. It's defined by the formula phi. Phi is 1 plus square root of 5 all over 2. And I think I also showed you in the last video that the continued fraction of phi has all ones in its continued fraction representation. Well, the metallic ratios are just like this, except instead of having just ones in their continued fraction, they have just some fixed positive integer n. So the nth metallic ratio is just defined as the irrational number such that all the continued fraction coefficients are equal to n. So in other words, phi, and we call them phi sub n. So phi sub 1, if you like, that's just phi. Usually leave the 1 out. That's just the ordinary golden ratio. And you can actually calculate a formula for arbitrary metallic ratio. So if you want all the nth metallic ratio, in other words, the irrational number where all the continued fraction coefficients are n, that's given by this formula on top. It's equal to n plus the square root of n squared plus 4 all divided by 2. And you can check when n equals 1. This gives you the golden ratio, 1 plus square root of 5 over 2. And you can see what it is for the first 5. I just list what they are and also their approximate decimal values. So the first one, phi, the golden ratio, is 1 plus square root of 5 over 2, which is approximately 1.61803. The second one, this is called, and by the way, I think the first 4 of these all have names. The first one's called the golden ratio. Second one, I guess you can kind of think of this like the Olympics. First place is gold, second place is silver, third place is bronze. So, as you might expect, the second of these metallic ratios is called the silver ratio. I guess the runner up, if you like, is uh, it would be 2 plus square root of 8 over 2, but you can divide, since the numerator is divisible by 2, you could just simplify to 1 plus square root of 2, and that's approximately 2.41421. And then you can keep going. The bronze ratio is 3 plus square root of 13 over 2. That's approximately 3 point, I can't read it with my glasses, 3.30278. Next one, the copper ratio is 2 plus square root of 5. Actually, there's an interesting thing about the copper ratio. It turns out to be the cube of the golden ratio. Don't ask me why, but it is. And it's approximately 4.23607. And finally, the fifth one, I don't think that has a name, but it's called metallic ratios after copper. I guess the metals get so cheap you don't want to keep naming them. They're just metals. So the fifth one is 5 plus square root of 29 over 2, which is approximately 5.19258. And you might wonder why these are interesting. Well, they're kind of interesting for the same reason as the golden ratio is interesting. Just like there's, I have a longer video on these metallic ratios you might want to watch, which I made several months ago. But just like Fibonacci numbers are related to the golden ratio, it turns out there's sequences of numbers that are closely related to each of these metallic ratios. For the silver ratio, the related sequences are Pell numbers. They're called Pell numbers. Starts out 1, 2, 5, 12, 29, 70. And then there's also what are called half companion Pell numbers 1, 3, 7, 17, 41. It turns out you can get very good approximations to the square root of 2 using these integers. And you can get good approximations to the square root of n for using the nth, the integer sequences corresponding to the nth metallic ratio. I'm not going to go into that today, but you can. So they have interesting properties, just like the golden ratio. But the golden ratio is the simplest one, and it's the most useful one. And I guess it deserves its title, the golden ratio. Gold is the most precious of all these metals. So anyway, that concludes my video for today on metallic ratios. Thank you for watching. Long live math, and I'll see you guys next time. Bye.